Hi, I'm Rebecca Weaver. I'm going to be covering section 7.2 in our applied calculus course today. We're covering partial derivatives. The first thing we need to do is look at the definition of a partial derivative, and that is the partial derivative of f of xy with respect to x is written as the partial of f with respect to x is the derivative of f of xy, where y is treated as just a constant, and f of xy is considered a function of x alone. The partial derivative of f of xy with respect to y is written as the partial of f with respect to y and is the derivative of f of xy where x is treated as a constant. So we're going to do an example. So let's compute the partial of f with respect to x, and then we'll show how to compute the partial of f with respect to y for f of xy equals x squared e to the 3x natural log of y. So to compute the partial of f with respect to x, we're only going to differentiate factors or terms that contain x, and then we're going to interpret y to just be a constant. So here's our function, and what we need to do is we have our x squared and we have e to the 3x. Now those two things are multiplied together, so we'll use the product rule, and that natural log of y is just going to plop him out in front just as if he's a constant. So notice here we are just taking the derivative of the x squared first, that's 2x e to the 3x, plus taking the derivative of e to the 3x is 3 e to the 3x times that x squared, and then you would just simplify it from there. Now to compute the partial of f with respect to y, we're only going to differentiate factors or terms that contain y, and we'll interpret x to be a constant. So all we have here is the natural log of y, so we're just going to take the derivative of that. And what we're going to get is just 1 over y, and then the x squared e to the 3x is just left as a constant multiplier out front. Let's look at another example. Let's say we have the partial of f with respect to L, and we have this function f, and he is a function of both L and K, and he equals 3 times the square root of LK. So since we're going to take the derivative of f with respect to L, we're going to treat every variable other than L just as a constant. So really, we're going to take that 3 onto the square root of LK, and we're going to say, well, that's just to the power 1/2. And then we're going to separate that so that each one is to the power 1/2. Now we can just take the 3k to the 1/2 and just say that's just a constant multiplier out front. Now we're going to take the derivative of just that L to the 1/2. So the partial of f with respect to L is we'll just bring that 1/2 out front, subtract the 1 from that 1/2 on the L, and we end up with 3 under the square root of k over 2 under the square root of L. You could simplify that a little bit to be 3/2 under the square root of k over L. All right, so evaluating partial derivatives at a point. We're just going to do as we normally would, and then we're just going to plug in those values for x, y, and z. So here we go. F of x, y, and z is xy squared z plus 5. We're going to evaluate the partial of f with respect to y at x, y, z, where x is 2, y is -1, and z is 3. We'll plug that in at the end. So let's take our derivative with respect to y. All we've got in there is a y squared. Everything else is a constant. So we're just going to take the derivative of y squared in there. So that's going to be 2 xyz. 5 drops out, plugging in our x, y, and z for the 2, -1, and 3. We'll get that our answer is -12. So here's our partial derivative rule. If f of xy equals e to another function g, and he's a function of xy, then the partial of f with respect to x is e to that same g function, and then we just take the derivative of g with respect to x. The same goes for the partial of f with respect to y. It'll just be e to that same g function times the partial of g with respect to y. So we can generalize the interpretations of the partial of f with respect to x and the partial of f with respect to y to yield the following fact. Let f of xy be a function of two variables, then if h and k are small, we have f of a plus h and b minus f of a and b is about equal to the partial of f with respect to x evaluated at ab times h. Likewise, if we have f of a and b plus k minus that f of ab, that's about equal to f, the partial of f with respect to y at that ab times k. So partial derivatives can be computed for functions of any number of variables. When taking the partial derivative with respect to one variable, we treat the other variables as a constant. So an example of this, let's let f of xyz be equal to xy squared z plus 5. Let's interpret the result of the partial of f with respect to y of where x is 2, y is -1, and z is 3, and that we found that that equaled 12. So we did that earlier. So let's interpret that. So we showed in the last example that it was -12. So this means that if x and z are kept constant and y is allowed to vary near -1, then f of xyz changes at a rate 12 times the change in y, but in a negative direction. That is, if x increases by one small unit, then f of xyz decreases by approximately 12 units. If y increases by h units, where h is very small, then f of xyz decreases by approximately 12h. That is f of where x is 2, y is -1 plus h, and z is 3, minus f of 2, -1, 3 is about equal to -12 times h. This is very useful. So let's look at an example. The demand for a certain gas-guzzling car, I love those gas-guzzling cars, is given by f of P1, P2, where P1 is the price of the car and P2 is the price of gasoline. So we need to explain why the partial of f with respect to P1 is less than 0 and the partial of f with respect to P2 is less than 0. Well, the partial of f with respect to P1 is the rate at which demand for the car changes as the price of the car changes. This partial derivative is always less than 0 since as the price of the car increases, the demand for the car will decrease and vice versa. The partial of f with respect to P2 is the rate at which demand for the car changes as the price of gas changes. This partial derivative is always less than 0 since the price of gas, as the price of gasoline increases, the demand for this car will decrease and vice versa. So let's let f of xy equal to x e to the y plus x to the fourth y plus y cubed. We need to find the second partial derivative of f with respect to x and with respect to y. Now we first note that the second partial of f with respect to x and y is going to just be, we're going to take the partial of f with respect to y, and then we're going to take that answer, and then we're going to take the partial of that with respect to x. This means we're going to compute it in a particular order, and we're going to take the partial derivative of f with respect to y with respect to x. A lot of with respect to. So first up, let's take the partial of f with respect to y. So let's find our y's. I've got an e to the y, and I have a x to the fourth y, and I have y cubed. There's a lot of y's in there. So let's take the derivative of each one of those independently. Those are fairly straightforward to just and treat the x's as constants. So we'll have x e to the y plus, taking the derivative of y is just 1, so that's x to the fourth, plus take the derivative of y cubed, that's going to be 3y squared. That's going to equal e to the y plus 4x cubed, because that x to the fourth, take the derivative of that, that'll be 4x cubed. Now that 3y squared, that's treated as a constant, so that's just All right, and then that is the end of this particular section. So if you guys have any questions, you be sure and email me, rweaver10@alaska.edu. Thank you very much.